Hello and welcome back. Today we'll be finding the area element, in other words, dx by dy or dy by dx, if you prefer in Cartesian, in polars. Of course, those who are doing a lot of work with that, is actually a very important fact, which unless you're being asked to prove, then you can use it without any further proofs or anything else. So this is what we're trying to prove, basically, that dx by dy is r dr d theta. I'm going to do it two different ways, and one is a proper proof, the other one's a geometric argument, which of course you get to see normally when you first meet this one. I don't know if this is going to be accepted, the geometric one, the second one, in an exam in university, obviously. You have to check with your own course. So we're going to do it first of all by Jacobians. So we want to find dx by dy, and this is the Jacobian matrix, dxy over d. Of course, in polars, the equations, I'm going to write them here, are x is r cos theta and y is r sine theta. So of course the variables in question now are r and theta, and thus of course we have dr by d theta. So this is now what we're trying to find. We're trying to find what is this scaling factor that this Jacobian will produce. And of course, looking at what we got up here, that's better because there's the dr by d theta, obviously. And of course, this will turn out to be r. So let's work out the Jacobian. That quantity here is a shorthand for writing this determinant, which is dx by dr, dx by d theta, and then we go dy by dr and dy by d theta. Got to excuse my cough. So dx by dr, dx by dr is of course equal to the cos of theta, dx by d theta, differentiating now this with respect to theta, is going to be a minus r sine theta. Dy by dr, that's simply the sine of theta, and dy by d theta, that's going to be an r cos theta. And of course, if we evaluate this determinant now, we're going to have an r cos squared theta from that, minus, which is a plus, of course, r sine squared theta, and of course the result follows. Okay, so we found that this quantity here is in fact r, and therefore dx by dy, the area element in Cartesian when we go into polars, is of course r dr d theta. I just want to show a geometric argument. Okay, oops, I moved the board, it appears. I hope it's in the same position. So we're going to do it geometrically by just the means of a picture. And as I said, in exams, please be careful, because I don't know if this is an acceptable proof. You get to see this, as I just said in the beginning of the video, when you first get introduced to polar coordinates. So this is now the picture. So we're in a polar system, and what we got in here, this is of course an area element. So this is now going to be a very small angle. So I want to be sloppy. I'm going to write delta theta, so take limits or anything like that. I'm going to jump straight into d theta. This is going to be r. That's going to be dr. And this is the area element, an infinitesimal, which has a tiny amount along the radial direction and a tiny amount in the theta direction. So this is my dx dy. and I want to know what is that in terms of r and theta. So I'm just gonna say here my dx dy is equal to the area of this sector, which is a half r plus dr all squared multiplied by the theta minus a half r squared d theta. I'm going to factorize a half d theta, and that's going to give me, I'm going to square this bracket, it's going to give me r plus 2r dr plus dr all squared minus an r squared. And this, of course, will give me a half. The r squareds cancel here, and I'm going to get a 2r dr plus dr squared, and I wrote the d theta back at the end. Now, dr all squared compared to 2r dr is of a much smaller order, so we can throw it away, and therefore that will be a half times 2r dr d theta, which of course gives us r dr d theta as before. So this is now a geometric proof if you prefer the geometry of that. It's all sound, it's just that it's more like a show rather than a proof. So if you have to prove the result, you have to go through the Jacobian matrix. I hope you found this useful, and for the time being, I'm signing out.